Continuing the discussion that we had about a point charge Q moving with uniform motion, and what we found was that uh, the electric field measured in a frame S bar relative to its uh, rest frame can be written as the electric field in another frame of reference, um, and the magnetic field in that other frame of reference. Conversely, the magnetic field in the frame S bar is a combination of the magnetic field and electric field in the other frame of reference. So what we find is that when we switch from one frame of reference, that the concept of electric and magnetic field starts to get all mixed up, or probably said in a better way, they merge. And so what we can do is we can look at the other components. By analogy, the z component and the y component, which are perpendicular to the direction of motion, should act the same way. So the z component of the electric field measured in S bar is gamma, the electric field in the z direction minus, or in this case plus, v by, and the magnetic field in the y direction measured in the S bar frame is gamma by plus v over c e z. So remember that gamma is 1 over 1 minus v over c quantity squared, square root, and the velocity v is the measurement of the velocity of basically the S bar frame with respect to S. Okay. So again, okay, so now we have those components, and now we have to ask ourselves, what about the X component? Well, we said before that the X component in one frame is equal to the X component in the other frame, because the special relativistic transformation of the electric field only occurs on perpendicular components, not the parallel components. So the electric field is going to be the same in the direction of the motion. Okay. So the only thing left then is the X component of the magnetic field. Okay. So unfortunately, in the parallel plate capacitor example that we used to derive this result, there is no magnetic field in the X direction. So we have to come up with another example, another analogy to help us fill in that last piece. And so what we're going to do is we're now going to not use a parallel plate capacitor, but let's say we have a solenoid. And this solenoid now is going to be moving in the X direction with some velocity v. And in this case, the magnetic field in a solenoid, the one reason why we've chosen it, is along the central axis. So now our magnetic field lines are going to be pointing in the direction of motion. Okay, so the equation for the solenoid in the S frame is mu0 n, the number of loops per unit length, times the current. And if we look at these two quantities, n bar, so the number of loops per length should be modified because there's a length in there. There's a length contraction. So in that case, we'd get gamma times n. And the current measured in the S bar frame should be different from the current in the S frame because current is charged per time. And if time dilation occurs, then what we should find is that 1 over gamma times the current in the S frame. Okay, so now what we can do is we can put those things in, and what we find is that the magnetic field measured in the S bar frame is just mu0 n bar I bar, which is mu0 gamma n times I over gamma. The gammas cancel, and what we have is mu0 n times I. So it turns out that the magnetic field in the direction of motion also does not change. So fields in the direction of motion remain unchanged. So now if we summarize this, we can write down the y components. So we would have gamma by plus v over c squared ez, and gamma ey minus v times bz. The z directions now, gamma bz minus v over c squared ey, and gamma ez plus v by. Okay, so now we have all the components of how they would be measured in each respective frame. So let's consider two cases. Let's say that there is no magnetic field in the S frame. Okay, so Bx equals By equals Bz equals 0. Okay, so now what do we get? Well, what we would find is that the B vector in the S bar frame would be gamma so Bx is 0, By, let me just write that down. So Bx is going to be 0, By would be, if we look up here at our what we have, By is 0, but it'd have an Ez, so I'd have a gamma v c squared Ez. Bz would be gamma minus v over c squared Ey. So that means that the total vector is going to be gamma v over c squared Ez in the y direction minus Ey in the z direction. Okay. Now, if we brought the gammas on the inside, what we would find is gamma EZY minus gamma EYZ, which, if we looked at that, because there is no magnetic fields in the S frame, those are just the electric field components. So we'd have EZ in the y direction minus EY in the z direction, all measured in the S bar frame. And so if you remember, the velocity is in the x direction. So what we come down to is B, measured in the S bar frame, is minus 1 over c squared, the velocity crossed into the electric field, as measured in the S bar frame. Okay. So let's take look at the case of no electric fields. So if E is 0 as measured in the S frame, then what we get is, so basically EX equals EY equals EZ. All of that is equal to 0. So that means that the electric field in the S-bar frame, similar to case number 1, would give us minus gamma V BZ in the y direction minus BY in the z direction. Because all of those electric field components in the S frame drop out, and all we're left with is the fact that the electric field is now equal to the magnetic field components. Okay, so we can play the same trick. Let's bring the gamma on the inside. So gamma BZ in the y direction minus gamma BY in the z direction, and we'd have minus z minus v, the velocity, times bz bar, measured in the s bar frame in the y direction, minus by bar in the z direction. And again, what we would get is the velocity crossed into the magnetic field. So what we find is that you have electric and magnetic fields which are perpendicular to each other. Actually, they're doubly transverse because the electric field is perpendicular to the velocity direction, and the magnetic field is perpendicular to the electric field. Okay, so we're going to take this knowledge, and in the next lecture what we're going to do is we're going to apply it to now come up with a new way of writing down fields into a much more compact form, because what we found is that electric and magnetic phenomenon, their observation of that, their measurement of that, depends on the frame that you're in. So in my frame, an electric field may look like an electric field, and in another frame moving at a velocity relative to me, that electric field actually produces magnetic phenomenon. And so we're going to come up with a new way, a mathematical way of writing all of this, which combines the electric and magnetic fields into one entity.